Thank you, John. My name is Kiyohiro from Seoul University of Science, Japan. Today, I'd like to talk about this theme. As shown in this figure, in most metallic materials, the flow stress during plastic deformation depends significantly on the strain rates. In this study, this relationship is defined as strain rate dependence. Cold spray is one of the coating techniques based on the severe plastic deformation of small particles at ultra high strain rates of more than 10 to the fourth power per second. So it's important to understand the deformation behavior of metallic materials at ultra high strain rates to improve the cold spray technique. The split Hopkinson pressure valve method is useful to measure the strain rate dependence up to this strain rate range. And so the several methods such as Terra impact test and ball impact test, including repeat, were developed for ultra high strain rates. This method provides variable data, however, have some limitations, including complexity and accuracy. Therefore, we developed a simple method for measuring strain rate dependence based on ball impact and indentation test that addresses the limitations of these conventional methods. In our approach to achieve high accuracy and practicality, all ball impact and indentation tests are designed so that the normalized indentation depth calculated as indentation depth divided by the ball radius remains constant, as shown in this figure. This allows us to achieve consistent work patterning across different experiments. Furthermore, we can easily control the strain rates by ball radius. In addition, the strain rate, inertial effect, and thermal softening are better modeled than in the conventional ball impact test. To further explain our method, I'll outline the theoretical framework. In ball indentation test, the plastic deformation energy is calculated as the area of the indentation load penetration depth curves. So the average flow stress during the indentation process can be simply calculated as this equation. Because inertial effect and thermal softening can be neglected in this situation. Then the average equivalent plastic strain rate in this study called representative strain rate can be calculated like this. In the ball indentation test, we only need to measure these three values. In ball impact test, the plastic deformation energy is calculated as the difference between the impact energy and the rebound energy. So the average flow stress can be calculated as this equation. We consider additional factors such as inertial effect and thermal softening. And then the temperature increase can be simply calculated as these equations. Because diabatic deformation can be assumed in these situations. Here's the average to flow stress is used was used instead of the actual flow stress. In the ball impact test, we only need to measure these three values. So our method is very simple. In order to validate our method, we performed a finite element analysis. This figure shows the schematic of the analysis model. The ball was assumed to be an elastic body, and the specimen was assumed to be an elastoplastic body, obeying the bilinear Johnson-Cook flow stress model expressed as this equation. The material constant C associated with the strain rate dependence is changed from C1 to C2 at to this strain rate. And the material constant used in this analysis is shown here. In the ball impact analysis, these three ball radii were selected to control strain rates. And then the ball indentation analysis, these two indentation velocities were chosen to control strain rates. And finally, the relationship between the representative strain rate and the average flow stress calculated by our method was compared with the input BJC model. This figure shows the relationship between the representative strain rate and the average flow stress. And the blue dashed line is the input BJC model. And these 2 points were calculated from the indentation analysis. And these 3 points are calculated from the ball impact analysis. As you can see, these values were close to the input BJC model. And then, as shown in the table, the material constants associated with the strain rate dependence were accurately determined by our method. In this study, we used the BJC model. However, our method is independent of the flow stress model. Next, we conducted ball impact and indentation tests. This figure shows the schematic of the ball impact test system we developed. The small balls with a diameter of 1 and 6 millimeter made of 5 carbon chromium bearing steel were accelerated by nitrogen gas through a long pipe, and then impacted onto aluminum alloy specimen at around 100 meters per second. The impact velocity and the rebound velocity were measured by these two lasers. This figure shows the relationship between impact velocity and the normalized indentation depth. As you can see, the normalized indentation depth is smaller for 1 millimeter balls than for 6 millimeter balls. Then the relationship between the impact velocity and the rebound velocity is shown here. The rebound velocity is higher for clearly higher for the 1 millimeter ball. This due to the influence of strain rate hardening. Next, we conducted the ball indentation test. We used the fatigue testing machine with 3 millimeter ball indentator and the indentation velocity was set to 3 micrometer per second. As a result, we obtain the indentation normalized penetration depth curves like this. As you can see, the variation between the individual curves is very small. And please attention here. The normalized indentation deficits were consistent with the impact test results. From these results, we calculate the representative strain rate on the average flow stress. As shown in this figure, the ultra high strain rate of more than 10 to the 5th power per second was achieved by the 1 millimeter ball impact test at 100 meters per second. And then compare these slopes, the significant increase in flow stress after the high strain rate was detected. In addition, the results of our method were close to the results of the conventional method we conducted. Consequently, our method is effective and practical for measuring the strain rate dependence. The conclusions are summarized here. Thank you for your attention.